So we make good use of the Laplace transform now, and because the mathematics you will see today is fairly horrendous, I would like to start with a bit of motivation that will put all of that math in the context of where and why we need it. You've seen in the PowerPoint presentations earlier in this module that in many cases your entire system or your entire control circuit is composed of distinct physical subunits. And what we don't want to do is to model the entire system with all of the complicated differential equations describing all of the interrelations there in one go, because that can be quite complicated. So item 1 for today is motivation. How we would like to deal with our systems and how we would like to simplify their description. So consider an individual unit. Individual reactor, individual integrator, individual measurement unit that has an input that is a function of time. That's our unit, we'll call it phi, and there's the output that comes out of it. What we know about such things is we can handle the differential equations governing this particular unit perhaps reasonably well, and they tend to be quite simple. What we then have, of course, is multiple things downstream and perhaps upstream. So there will be another system called psi here that outputs some other signal, z of t. We would like to be able to chain such systems in a straightforward way that is similar to just little puzzle pieces, without having to worry about necessarily how the entire collective system would behave at the level at which we consider this. You will also remember that the solutions to those differential equations were quite nicely expressed if we work in the Laplace domain. It should be a reaction to the input to the system z, y of s, and the reaction pertains to the system psi. And then we have the reaction pertaining to the system phi of s coming from the system psi of s coming from the input. And that should be phi, and that should be psi. So the final output of our chained system is a reaction to the input of the system psi. So that's the input, that's the transfer function of system psi, and the output y comes out of the system phi. So it is the reaction of the system phi to the input that comes in. And as you can see, in some ideal perfect world, we would like such transfer functions to just stack multiplicatively. So today is about the conditions under which something like that is possible. And the condition is for the systems to be what mathematicians call linear time invariant, LTI systems. And you've seen already in what the chemical engineers have shown you, in fact, examples of these transfer functions, and I think the word LTI was mentioned to you in some previous lectures. But let us consider this now formally. So a system phi is called linear time invariant if firstly, it is linear. So if we put a linear combination of signals into the system, we should get the corresponding linear combination of outputs. So phi acting on alpha x1 of t plus beta x2 of t. so a linear combination of two inputs, x1 and x2, should return the corresponding linear combination of responses to x1 and x2. This is called linearity. The second thing it must do is, if we send the same input tomorrow as we had sent yesterday, we should get the same output, except correspondingly time shifted. So if we take phi and then of x of t minus some time t naught, then we should get the output that is correspondingly shifted, such that this y x of t is y of t. So this input and this output were yesterday. This input and its output are today. So let's say t0 is 24 hours. The system must return the same output. So linearity, time invariance, the system is therefore called LTI, linear time invariant. So under these circumstances, and only for zero initial conditions, so plus zero initial condition, so the very first x at time 0 must be 0, this is true. So we can daisy chain systems like that. I will not give a formal proof of that statement. That's an exercise too far for a second year undergraduate course. But in order for something like this to be possible, the system must be LTI and it must have a zero initial condition. Okay, of course you will immediately argue that, well, zero initial conditions are virtually unheard of in practical engineering. In fact, in most cases that would not be the case. So how do we reformulate our mathematical problem to obey this property? And that's the third topic on the agenda, and that's deviation variables. So let us go through a practical example, and it will illustrate both this principle here and the concept of deviation variables. Let us consider a buffer tank. So we have some density rho and volume V, and then d by dt of some output concentration as a function of time. And you know that in a buffer tank we have the outflow with outflow rate W, then the concentration at the outflow, and that will be a function of time. And then we have the inflow, so we have W in, time independent, and then X in that depends on time. And of course the role of such buffer tanks is to smooth out variations in the input concentration. We have some volume. This input concentration can vary, with some noise in it, for example, and the outflow, hopefully for the tank of sufficient volume, is significantly smoothed out in the temporal variations of the concentration. Okay, but let us try and reformulate this in a way that would follow something like this. So we would like the Laplace transform of the outflow to be related multiplicatively to the Laplace transform of the inflow. Let us see if that's even possible. We use the content of the previous lecture to just transform that into the Laplace domain. So we have rho v. Remember what the Laplace transform of the derivative was. It was s x of s minus x of 0, and then that is minus w out x out of s, and this is out, then plus the inflow rate times the Laplace transform of the inflow function. Well, if we attempt to express x out as x in multiplied by something, we will discover that that is not possible. And the reason for that is this initial condition term here. Let us actually just do the transformation and demonstrate that that's not the case. So what we are going to have is rho v s x out of s. I will move that term over there, so minus omega out becomes a plus of s equals, and I will move that, so rho v x of 0 plus w in x in of s. And so if we didn't have this initial condition, then we could, right, so simply just divide by that plus that, have a multiplicative relation of the output to the input, but this thing gets in the way. How do we solve this? Let us consider these variables not as absolute quantities, but as quantities that are relative to some hypothetical steady state, to some reference values. And then if we have a steady state of that tank, then we can just choose it to be our next 0 point, right? And the deviation from the steady state would then initially be 0, and that would satisfy our initial condition property here. Okay, how do we find the steady state? Well, we consider the dynamics of our tank, and let's consider the dynamics in a situation where we have some average value here, some average value there, and as a result, the tank has settled and the derivative became 0. So, hypothetical steady state, is 0 equals minus w out, and then some steady state outflow concentration plus W in times some steady state inflow concentration. And that is the definition of it. Let us now take this equation and subtract it term by term out of that equation there. So we are going to have rho v d by dt x out of t equals minus omega out and then x out of t minus the steady state value, and then plus rate in and then x in of t minus the steady state value. Notice, however, that we can also do it to the derivative. If I subtract a constant underneath the derivative, well, derivative will simply destroy the constant, so it's going to be exactly the same equation. So I will also subtract x out steady here. And let us rename our variables. We will say, okay, our y out of t is x out of t minus x steady state, and our y in of t will be y in as a function of time, x in minus x in steady. These are called deviation variables. Plug them in, and then let's try again, expressing it in the form that we require there. What we have now is rho v d by dt y out of t is minus omega out y out and then plus omega in y in. The Laplace transform of this would not have this problem if we had assumed that the tank was initially in the steady state. Okay, so initial conditions, steady state. Or in fact, if the tank had been in some other initial condition, we would accomplish the same result, achieve the same result by subtracting that initial condition as the reference point. So these are deviations from the initial condition. We just chose the steady state as the initial condition. Okay, so Laplace image of this expression is then rho v s y out of s equals minus w out and then y big out of s plus w in y big in of s. And this is easily soluble for y. So the result is y out of s is going to be. So I move that thing over to this side, take y out of the bracket, y out of the bracket, and then divide that in. So we would have w in over rho vs and then plus w out and then y in of s. And we have achieved our objective. We have the Laplace transform of the input. We have what is called a transfer function. This is our h of s. It multiplies the input and produces the Laplace transform of the output. And if we have subsequent systems which are receiving the output of this buffer tank that follow the same LTI mathematics as this system does, we will be able to sequentially multiply with their corresponding response functions. And you can see how one can then have a palette of pre-calculated response functions. Every little module that you have just comes documented with a response function that this has, and then if you know the input at the very beginning, you would be able to quickly calculate the output at the very end. We use it a lot in radio spectroscopy, where we first have the frequency synthesis, then we have the amplifier, then we have the probe, and what the sample sees is just a combination of all the transfer functions of every piece of equipment, and in fact every cable that is in the way, because they also modify the inputs somewhat. Okay, so that is a basic example of this approach that we have just decided to use, and secondly of the concept of the deviation variables. Okay, let us do a bit of a notational transformation here as well. We will introduce the flow ratio, and it's just the ratio of the inflow to the outflow. So we have K is W in over W out. And what we will also do is we will introduce the characteristic outflow time, so the time that it takes for the tank to empty, and that would be tau, and that is rho v divided by the outflow rate. And with that in place, this gets simplified and becomes k over tau s plus 1. So you can see in the denominator we have the index of the exponential, giving the time scale of the processes that we are dealing with, and in the numerator we have the amplification coefficient. So if our inflow significantly exceeds the outflow, this will be large. If it's the other way around, it will be small, and tau is just the characteristic time it takes the system to respond to any alteration in the input concentration. Okay, now this is of course a system with just one input and just one output. Let us consider a situation where we have multiple inputs and multiple outputs. So starting with just multiple inputs, so for multiple inputs, and you will see the power of this transfer function formalism, because these inputs, when the dust has settled on our mathematics, will combine quite nicely and in fact retain the simplicity of this formalism. So we upgrade our flow tank that was previously a buffer, and we make it a blender. And you know what happens in a blender tank. We have multiple inputs, both with some flow rate, and we have a single output, and the purpose is to regulate the concentration at the output. So same mathematics, we have rho v, then d by dt x out of t, the derivative of the outflow concentration, and then minus outflow rate x out of t plus the now two inflow rates. So we have w1 in x in first of t plus w in second x in second of t. Two concentrations and two flow rates at the inputs of the tank. Exactly the same thing would happen if we were to Laplace transform this directly. We would have this pesky initial condition preventing us from having a neat multiplicative relation like that one. So what we need to do is to find deviation variables for this more complicated case in exactly the same way. So we say, okay, consider a hypothetical steady state corresponding to some average values of the outflow concentrations and the inflow concentrations, which would make the tank settle and therefore put the time derivative to 0. So that would be minus w out, then x average out plus w in first, x average in first, plus w in second, x average in second. Subtracting element by element from this equation and introducing deviation variables. So our variables are going to be, well, 3 of them now, but y out and 2 y ins, which have these steady state values subtracted out. So y out of t is x out of t minus the steady state value, and then x in, or rather y in, now it's a deviation variable, 1 or 2 of t is x in 1 or 2 as a function of time minus x in 1 or 2 average. And these will be our deviation variables. We plug them in, we do the Laplace transform. So after all of that happens and the dust settles, we have rho v s, then y out of s equals this entire right hand side. So that is x of s, x of s, x of s. In the deviation variables they become y. So minus w out y out of s plus w in first, y in first of s plus w in second, y in second of s. And let us try and express the Laplace transform of our output in terms of these Laplace transforms of the input. So I take this first term after the equal sign and I push it over to the left-hand side, and I keep those things unchanged. So what we are going to have is rho Vs plus W out times Y out of S equals this left-hand side. So W in first, Y in first of S plus W in second, Y in second of S. And finally, we can just divide by that denominator, and an interesting thing will transpire. You will see that in the Laplace domain, the two inputs act additively with their corresponding transfer functions. So our Y out of S is going to be W in first, rho Vs plus W out acting on the first input, plus then W in second, rho Vs plus W out acting on the second input. So previously here we had one input, it got multiplied by the transfer function and produced one output. Now we have two inputs, they are multiplied by the two corresponding transfer functions and they produce our output. If we extend this to a situation where our system has multiple outputs as well as multiple inputs, what is going to happen is we will have multiple Y outs, multiple Y ins, and for every Y out and for every Y in we will have this term in front describing in Laplace domain how the corresponding input affects the corresponding output. As you can see, this is more or less just arithmetic. In Laplace domain, this is significantly easier to deal with than solving a system of coupled ordinary differential equations. And what is very important is that system of equations might be case specific, might be topology specific, how your individual inputs are connected to your outputs, how the subsystems fit together. This will all change your differential equations in a way that is hard to monitor and hard to integrate into some kind of automated modeling situation. These transfer functions combine quite nicely. For multiple inputs, they're additive. For sequentially changed systems, they're multiplicative, and so quite easy to deal with and quite easy therefore to obtain analytical solutions for entire classes of systems and topologies rather than for anything specific that a numerical solution of a differential equation might then produce. Okay, so this is multiple inputs and outputs. Finally, consider a situation where our system is not in fact linear. So systems that break at least this first condition. What can we do with them? Because that was an essential requirement for something like that to be possible. And so the next item on our agenda, item 5, is linearization. We say that we hope, even though the system is strictly speaking non-linear, that its small deviations from some steady state or from some reference values might nonetheless be linear. This is quite a common situation because normally you don't want your reactor to be all over the place, you know, to operate in a couple of orders of magnitude of pressures and temperatures. It is rarely necessary. You want your reactor to settle in and do its thing. And you want it to respond to minor variations in the input parameters by trying to return to its steady state as fast as possible. So in fact, minimal deviations from some operating conditions might be your objective. And so even though the system is nonlinear, deviations you are practically dealing with might be small. So let us express that formally. We have our dx out by dt, for example, in one of these mixing tanks, being some horrible nonlinear function of everything. It will be some function that depends on x out and depends on x in from all the inputs. So x in 1, x in 2, and possibly others in some non-linear way. We don't even know what it is. Could be exponential, could be polynomial, but significantly nonlinear. What we do, however, require, and physics usually provides, is for this function to be differentiable. Enough times for us to have a Taylor series. And I will now remind you from your mathematics course what a multivariate Taylor series was. So, reminder, if we have a function f of x, y, z, and possibly other variables, then we have some reference point, x naught, y naught, z naught, and so on, then this function is equal to its value at the reference point, and possibly others, plus its partial derivative with respect to x computed at the reference point times x minus the reference point, plus its partial derivative computed at the reference point with respect to y, then the difference with the reference point in y, plus so on, plus terms with higher derivatives. So first derivative with respect to every variable, and then every combination of every higher derivatives times the corresponding powers. So this can be quite complicated, but we assume that this linear approximation is a good approximation. So we have our function, and it is modeled adequately by the slope with respect to x times x, slope with respect to y times y, and so on. We essentially assume that if it's a one-dimensional function, it is well approximated by a tangent line. If it's a two-dimensional function, it's well approximated by a tangent plane. And if there are higher dimensions in there, then a good approximation is to take a tangent hyperplane in the space of a higher dimension. At that point, the right-hand side becomes linear again, and we are allowed to use all of this mathematics again. However, the additional stage is that we must obtain this Taylor series first. So let us go through an example of this process. It is also quite mathematically involved, so I'm taking it for you to put me on pause, catch up, and then unpause me and continue listening. Let us clear up some space and look again at our buffer tank, but this time we will have a time-dependent inflow rate as well as a time-dependent concentration. So upgrading the tank yet again to allow it to change the W in, to make it a function of time. So same old tank, and now we have rho v d by dt x out of t is minus W out x out of t plus W in as a function of time times x in as a function of time. So this is the difference, right? So this term is not linear, it's bilinear now. There is a multiplication, which in this case is a nonlinearity that couples the input w in to the input x in. And so this particular relation breaks, and I think the time invariance also breaks if you look at it. Okay, what do we do? Well, the first thing we must do is linearization. So we must use the Taylor series to expand that around some reference values and obtain it in a linear form. So our reference values are going to be the usual. We have x out average, we have the average inflow rate, and we have the x in average. And these will be our x naught, y naught, and z naught for the Taylor series. Our nonlinear function, f, depends on three parameters. It depends on x out, it depends on w in, and it depends on x in. So x out, w in, and x in. And that function is minus w out, which is still a constant, times x out plus w in times x in. Three variables, thankfully quite simple. The next stage is to get us the Taylor series as prescribed there. So our f of x out, w in, and then x in is approximately equal to its value at the reference point. So that goes in, that goes in, that goes in, minus w out, then x out steady state, plus w in steady state, x in steady state, then plus its partial derivative with respect to the first variable. So partial derivative with respect to x out, it's equal to minus omega out. So minus omega, not omega w. I just deal with omegas too much in my life because I'm doing quantum mechanics for a living. So w out, then the value of the difference between the variable and the reference point, so x in minus x in steady state. Then the partial derivative with respect to the second variable, so partial derivative with respect to w in, that disappears because it doesn't depend on it. If we differentiate this with respect to w in, we get x in plus x in, and computed at the reference point, so x in reference, and then w in minus w in reference. Partial derivative with respect to the third variable, derivative of that with respect to x in is w in, and then the third variable minus the reference point, x in minus x in reference. This actually simplifies. If you look at it carefully, we have minus w out x out here. This should be out, of course, and then out, and then we have it with a minus, and we have it with a plus. So minus and minus gets us a plus, so that cancels. Then w in x in, here with a plus and here with a minus, that also cancels. And then we have our function linearized. We have minus w out x out, and that Remember, W out is a constant, so it's a constant times a variable, plus X in steady state, W in, again, that is a constant and that is a variable, plus finally that term, and that's omega in steady, and then X in minus X in steady. So notice that everywhere we are either in the deviation variables already, like here and here, or we have them appearing automatically. So this is linear with respect to X out, this is linear with respect to W in, and that is linear with respect to X in. The problem has been linearized. And so all of the mathematics that has pertained to the treatment here becomes possible, except after the dust has settled on it, there will be three variables there. There will be Y out, there will be Y in, but there will also be W in. And so our Laplace transform of the output will depend in exactly this way on the Laplace transform of the input, but also on the Laplace transform of the flow rate. So I will not produce any more horrendous mathematics on the board. You have this corresponding expression, which looks literally like this, except that is the input and that's the flow rate that we have there. The principal condition being, of course, all of these deviations from the steady state have to be sufficiently small for this Taylor series to be a good approximation. If they're not, this entire theory would break down for the nonlinear system. Okay, so final topic is pulse response. And this has an interesting practical visualization. Imagine you are trying to tune a church bell. How do we tune bells? Well, there are two possible ways that one can think of. One is to hang the bell like that. Have a speaker, output every frequency in turn, just scan the frequencies. And then have a microphone here, recording the volume of the sound. If we transition through the frequencies at the points where the bell resonates, resonance means the bell starts moving mechanically. Moving mechanically means it's converting this energy into heat. We will see absorption of energy. So if we plot that absorption as a function of frequency, we will see peaks of absorption corresponding to the resonant frequencies of the bell. And by altering its geometry, shaving bits and pieces there, we can then get rid of the unwanted frequencies and keep the wanted ones. But this is clearly a very slow process. So what the bell tuners actually do is they do not do it like that. What they do instead is they hit it with a hammer and record the resulting sound. Of course, it stands to reason that when we hit the bell with a hammer, the sound that comes out contains all of the resonance frequencies of the bell. So what they record is acoustic pressure as a function of time, and that will contain all of the frequencies. And then they use a Fourier transform, so a way of converting a time domain signal into the corresponding table of frequencies to get that data. Notice what is happening, however. This strike by a bell is a very sharp, very brief input of energy into the system. which in some way produces the entire frequency information content in one go. So the first thing we need to do is to formalize this bell strike mathematically, and second is to explore mathematically why it is that after a bell strike we suddenly get all of the information about the system in one go. So item A here is Dirac's delta function. And it's an interesting function. It's a function that is 0 everywhere except one point. So delta of t, that's t. It goes as a 0, then it is infinite at the origin, and then it is 0 again. At the same time, however, the integral of delta of t dt is equal to 1. So even though it's only non-zero in just one point and it's infinite in that point, it nonetheless integrates to 1. And the way to understand how that's possible is to consider a sequence of Gaussian functions. If we have a Gaussian with unit area, quite broad like that, well, it has a unit area. Then we can make the Gaussian a bit narrower but keep the area. Of course, as a result, it would need to become slightly taller. So it would be something like that, but still a unit area. And if we shrink it and shrink it and shrink it, at some point it becomes really tall, but still retains the unit area. And if we go to the limit of infinitely narrow Gaussian, it will become infinitely high but still retain a unit area, and that limit is called the delta function. Now, if we use that to hit our system, we will also have to take advantage of one particular property of these delta functions. Let us think about what would happen if we multiply a delta function by some other function, f of t, and take the integral. Of course, delta function is 0 everywhere. The only place where it's not 0 is here, and so our infinity will get multiplied by the value of the function. This integral will correspondingly become equal to the value of that function. And so the delta function has a lovely property that its value, so integral minus infinity to infinity f of t delta of t dt is f of 0. It's just cutting out the value of the function at the origin. And if we start shifting this function, what we will arrive at is the following property. F of t is integral minus infinity to infinity f of tau delta of tau minus t dt, or rather in this case, this d tau is this f of t. So in essence, what happens if you shift this delta function left or right, it cuts out the corresponding values of our function which it multiplies, so the so-called convolution property. Okay, what is this useful for in the context of our linear time-invariant system? Well, let's feed that signal into the LTI system. So we have some phi, and we send f of t through it. Let's represent it by this integral. So we have phi now acting on integral from minus infinity to infinity f of tau delta of tau minus t d tau. Because the system is linear, we can swap the action by the system and the integration, right? Because the integration is also a linear operation. So we can get our system under the integral. The second thing that we can notice is the system only acts on functions of real time, not on functions of integration parameter. And so we can take f of tau out of the bracket as well. So the result will be an integral from minus infinity to infinity f of tau and then phi acting on delta of tau minus t d tau. And it takes some thinking about this, but this is a remarkable relation. This is the response of our system to the hammer strike. It's called the pulse response. That is some function that we want to see the response to. So what I will call that is h of t minus tau minus t. And of course the system's time invariant, so we can actually have these time shifts. So the result is this, minus infinity to infinity f of tau h of tau minus t d tau. It turns out that the response of our system to any conceivable input is just the convolution of that input with the pulse response. So the pulse response in principle contains complete information about what our system is. We don't need to solve any differential equations again. We don't need to look at any of the dynamics. The only thing we need to have is this pulse response function. And so in a lot of cases when you buy equipment, you will in the documentation see this pulse response written down, either analytically or numerically. And then of course whatever input you are sending in to obtain the output, you just need to get this integral done. And that is one final property that I wanted to mention about the LTI systems. Okay, so this is a lot of mathematics to take in. Be ready, it will take a few weeks to shake down in your heads, because I've sort of exposed you to the fairly significant amount of unfortunately necessary algebra. But this is how you will be dealing with chains of your engineering systems from now on. In fact, you already have. I have looked through your handouts for the previous lectures, and nearly every page at some point has something that looks like that or has a quadratic in the denominator. Those were response functions that Mohammed has shown you for the corresponding blocks that he was considering, except he just, yeah, okay, that's the response function, and he probably did not explain it at the time. But this lecture is where they are coming from and why they are coming from. Okay, the summary. Laplace transform, because it maps differentiation into multiplication, also maps the action by a linear time invariant system if you've chosen your variables well into multiplication. You have some input here, first input of the system, you have the second input of the system. Every input will come associated with its corresponding transfer function. You take all of the inputs, you multiply them by the corresponding transfer functions, you sum them all up. That is the Laplace transform of your output. However long the chain, however complicated the number of inputs and outputs, if these fairly lenient LTI conditions are satisfied, you can model the system like that. Even for nonlinear systems, if the nonlinearities are slight, or you are not venturing too far from some equilibrium around which the Taylor series is a good approximation, then you can still do that, although you have to put in a little bit more sweat to linearize your system in the vicinity of the steady state that you are hoping not to stray too far from. All right, that's me, and let's do the problem set, and hopefully it will become a bit clearer once you've done that.